Hello, I'm Cătălin Hriscu from the MPI for Security in Bochum, and I will tell you more about my group research on formally verified security. So what we mean by formally verified security is that we start our research usually by setting clear security goals, so coming up with mathematical definitions. What does it mean to be secure in a certain setting? Then we devise security mechanisms that are tailored at achieving those precise security goals. And finally, we prove that the enforcement mechanisms do indeed achieve the security goals using proof assistants like ROC and F-star. And in settings where formal verification is not possible because we are looking at very big artifacts, we also look at property-based testing using tools like QuickCheck. So I will illustrate this on an example from a couple of years ago, a project on secure compilation of compartmentalized C code. In this case, the security goal we set was on restricting the scope of undefined behavior to just the compartments that were compromised. In terms of enforcement, we devised a variant of ComCert that targets Cherry, which is a security architecture which enforces security using capabilities. And finally, we devised machine check proofs in the ROC proof assistant that our C compiler does indeed achieve secure compilation. And in order to achieve this, we devise more scalable proof techniques. So this is an old project. What we're doing at the moment is, for instance, secure compilation against speculative execution side channels like Spectre. In this setting, the goal is relative security, so showing that speculation doesn't cause extra leaks with respect to an execution of the source program without speculation. The way we are achieving this is using a new variant of speculative load hardening, which is a software defense combined with Intel CET, which is a hardware mechanism for control flow integrity. And we have ROC proofs in simplified settings that these mechanisms do indeed achieve relative security. And at the moment, we are working on scaling up these results to LLVM and x86. And this is a setting where really formal verification is not possible at such a large scale. And we are looking into property-based testing as a way of achieving assurance. Finally, I was one of the designers of the F-star proof-oriented programming language. And what we are doing at the moment is devising a secure compilation chain for verified F-star programs. And we are proving the security of this compiler using F-star itself. And we are making increasing use of coding agents like Claude to do these proofs. In the recent months, Claude and other coding agents have gotten very good at doing proofs, which saves us a lot of work. Then the main idea behind F-star is something called Dijkstra monads. And this was devised for proving the correctness of programs. And now we are looking at using the same ideas for finding bugs, using ideas for incorrectness logic. And also we are working on porting the ideas behind Dijkstra monads to the Lean proof assistant, which is a new proof assistant that has better support for automation and also good support for coding agents. So this was a quick summary of my group's research on formally verified security. Thanks for listening.